Hello everyone for this new iteration of the Kokkos Tea time. Sorry for the late advertising about this session, and let me wish you a happy new year, and I hope you will have a lot of parallelisms and threads this year. Um, the talk today is about Kokkos Comm. It's presented by Gabriel Dos Santos, that is a Ph.D. student at CA. He will soon begin his third year of Ph.D. He's a former student of Université de Versailles-Saint-Quentin in France, and he will present part of his work during his PhD around Kokkos Comm. I'll let you present your slide, Gabriel.
Yes, so hello all. So as Cedric said, I'm going to introduce Kokkos Comm, which is our attempt at building a performance portable communication interface for distributed Kokkos applications and the broader Kokkos ecosystem. So I want to start with a quick disclaimer to thank all the Kokkos Comm core contributors, so mainly at CEA, Sandia National Labs, and Tennessee Tech, who have helped with reviewing these slides before I present it to you. So we'll start with a little bit of context around this effort. Then we'll go over some of the design work that we've done to actually write this API, this interface. Then I'll go into presenting Kokkos Comm properly, the project itself. We'll talk about some future work, what's planned next, and we'll conclude. So I wanted to briefly remind people of the Kokkos programming model. I know most folks here are familiar with it, but I thought it was a good reminder on what are the challenges when integrating Kokkos and distributed communication models. So Kokkos is really two parts. One is the multidimensional arrays side, which are in the form of the Kokkos views. So it's purely how we interact with multidimensional data. And Kokkos proposes some uh, different ways to see that data. So first, there are memory spaces, which describe where the data is being stored. Then we have memory layouts, which describe how that data is being stored in memory. And then we have various memory traits, which allow us to tune and fine tune the behavior on how we access that data. And the other part of Kokkos is its parallel execution model, which allows us to describe where the execution is happening. So that's the execution spaces. Then we have execution patterns. What are we actually executing? So that's the main primitive that Kokkos provides, which are the parallel for, parallel reduce, and parallel scan primitives. And then finally, we have execution policies, which describe how we are going to run that computation. So when interacting with between Kokkos and a distributed communication library, we need to think about how that communication library is going to interpret that these Kokkos views, the multidimensional arrays, and how does that these communication operations interact with the parallel execution model of Kokkos. So today, how do we do the distributed computing with Kokkos? Mainly, it's hand-rolled. There's no native support for explicit communications, and generally, people do it with MPI. And what we are seeing is that Kokkos and MPI, the interfacing logic is unique to each project or application that uses Kokkos and wants to distribute across many nodes. So there's lots of code duplication across the Kokkos ecosystem, and we see different approaches and implementation strategies to how we handle some of these technical challenges and special cases that need to be handled. So what are these technical challenges? The first question is, how do we pass a Kokkos view to MPI? And we need to ask ourselves, how do we handle non-contiguous data? What is the strategy to exchange that data over the network? Do we use packing and unpacking of one big contiguous packet? Do we rely on custom MPI data types and let the MPI data type engine do the work? Or do we just send multiple small but contiguous data packets? Then, what if the MPI implementation isn't GPU aware? What's the strategy? Generally, we'll do host staging. So views that are stored on the device are being copied on the CPU, and then we perform an MPI call on the views that have been copied on the CPU. So that's mainly the interaction on MPI and Kokkos view, so that the data part of Kokkos. And then how do we deal with the Kokkos views lifetimes? So how do these interact with the Kokkos execution model and the communication provided by MPI? What's the interaction between the two? And how do we make sure that asynchronous parallel computations and non-blocking MPI communications that operate on the same Kokkos views are consistent with one another? So if we take a look at an example of how we would wrap MPI iSend, so the non-blocking version of MPI send, the first thing that we need to do is here deduce what is the view type, what's the value type of the view. Then we need to handle GPU awareness. So if your MPI implementation isn't able to do GPU aware communications, you need to bring the device view on to the host and perform the MPI communication. Here it's elided. I'd only just have the comment on you would need to do that. Then if you have an MPI that is GPU aware, you need to care about, is your view contiguous or not? If it's not, then you need to process that. And if you're on the happy path, you would just fence on the provided execution space. So make sure that there's no ongoing work in that execution space before performing the actual MPI call, MPI iSend call. So it's not very difficult, but there's lots of things that we need to think about, that we need to care about. And when you do that on all the MPI calls that you want to wrap, that's a fair amount of work. So next, on to the design phase of Kokkos Comm. So our challenges are to how do we expose an API that allows Kokkos and MPI interoperability, that is able to handle MPI GPU awareness, that handles non-contiguous data, that facilitates views lifetime management, and that as well doesn't introduce too much overhead, and if possible, not at all. And our second question that was, can we also design that API to work with other communication libraries? So not only MPI, but also GPGPU or AI-oriented libraries such as NVIDIA Nickel or its equivalent at AMD, which is a Recall. And also other communication libraries that are much closer to the hardware or the interconnect technologies, such as libfabric, OFI, or UCX. So the objective of Kokkos Comm were to first try to come up with a high-level, compact, and composable API that really abstracts the different concepts that are common between the underlying communication libraries, that is able to handle all the special cases I've mentioned previously, and try to really minimize the interface. So we only want to expose a subset of the point-to-point and collectives, really with the goal of making the library easy to use, but hard to misuse. Our second goal was to leverage innovations in recent standards revision. So first in the C++ language, in C++ 20, which is the standard used by Kokkos 5.0, There's lots of advancements on compile time guarantees, meta programming techniques that we can really leverage to make the code safer as well as fast, avoid any necessary overhead. And there are also additions to the standard library that we want to explore. So these are not necessarily in C++20. We have MD-span, which is more or less the standardization of Kokkos views. Stud execution, which is coming in C++26 for asynchronous execution. Stud expected, which is in C++23 and extended in C++26 for nicer error handling. So these are additions that we want to explore on the C++ language side, but also on communication libraries. So there are some that are MPI specific. So for example, MPI sessions, persistent or partitioned communications, and other which are shared between communication libraries such as stream triggering, device initiation, etc. And finally, our last goal, third and last goal, was to, in the same spirit of Kokkos, really maintain performance portability. Today, we have very complex systems with CPUs, multi-GPUs, and multi-NICs on a single node with different interconnect technologies, and we want to guarantee some performance portability across these different hardwares, and also prepare the future for smart NICs. So Nickel is a very good example of a library that achieves a lot of these goals. So it's a message passing communication library designed for NVIDIA GPUs. So it's written in C++, but there are lots of C99 style of writing. So it doesn't leverage all the niceties that, let's say, that modern C++ brings you. It's optimized for mainly device-to-device communications. So in particular, patterns that you find in AI applications. So its API is very much based on MPI, but highly streamlined. It's very much simplified. It's implemented as CUDA kernels, and you will synchronize on these communication operations the same way that you would synchronize on a stream or in an event. And it's designed to be collectives first. So by default, Nickel provides broadcast, all gather, all reduce, scatter, which is reduce scatter block for MPI, and reduce. And since September of last year, gather, scatter, and all-to-all collectives were added. So it has very minimal point-to-point support, only send and receive. So it's very simplified on that front. And also limited data type support. So for example, there's no support for complex floating point. You don't have the possibility to create custom data types as you would with MPI. But in contrast, you have support for reduced floating point precisions that you find in AI applications. So now let's introduce Kokkos Comm proper. So a brief overview of the development framework. The project was started in March of 2024, so it's coming right about 2 years now. It's a collaboration between mainly the CEA, Sandia National Labs, and Tennessee Tech, with other institutions that have participated sporadically. The project is hosted by the Kokkos organization, so it's an official Kokkos project. And by extensions, we are a member of the HPSF and Linux Foundations, and everything is done on GitHub. We have dedicated discussion channels that you can reach us on. So on the Kokkos Slack, there is the MPI interrupt channel. We also have discussions and issue pages on the GitHub repo, and there are bi-weekly developer meeting on the HPS. So it's happening on Thursdays. It's at 16:30 Central European time. So that's, I believe, 10:30 Eastern in the US. And next meeting is next week. So on Thursday, the 29th of January. This is the Kokkos stack, how we would like to have Kokkos Comm when it's production ready. So applications can sit on top of Kokkos for the computation side to have performance portable computation with different backends that are able to target compute hardware. And Kokkos Comm is here to provide performance portable communications and is able to target vendor specific interconnects or networking hardware. So on the Kokkos side, you have OpenMP, CUDA, HIP, SQL, etc. And Kokkos Comm, you have MPI, NIC-ORented, RCCL, oneCLL backends that are able to target the various vendors. So some technical choices that we wanted to discuss. So we are keeping a model based on message passing, so two-sided explicit communications, as opposed to what Kokkos Remote Spaces does. It's very much a distributed shared memory space for Kokkos views. And everything is implicit. It's a one-sided model. Kokkos Comm is written in C++20, so we are trying to leverage compile time meta programming techniques, and especially constexpr, to minimize overhead and do as much compile time decisions as we can, so that the end code is the critical path in the library is pretty straightforward once the code is compiled. We are a purely non-blocking API. This is to enable computation and communication overlap. Without it, you can't really do it. And it also helps to expose how the execution model of Kokkos for computation and the non-blocking communications can be run concurrently. So it's a very important aspect of Kokkos Comm in that regard. And a last point that we wanted to mention here is that we are forbidding calling Kokkos Comm from within a parallel region, so a kernel. You can do it on some combination of Kokkos backends and communication libraries. So, for example, you could do it with OpenMP backend and MPI. But if you're running with MPI and CUDA backend, then you can't call an MPI function from within a kernel. So we're deciding not to allow it at all. For now, it's not detected by Kokkos Comm because Kokkos doesn't have the means to tell us if we're running a parallel region or not, but it should be coming. So for now, it's undefined behavior if users do it anyway. The second part of our technical choices is that we really want to implement only the high-level logic. So we are trying to resolve the challenges that I've mentioned at the beginning of this talk, but we are not a runtime. So we're not trying to re-implement collective algorithms, for example, or trying to do low-level network management. And this also ties in with the goal of minimizing the overhead. So we don't introduce any runtime needs in Kokkos Comm. However, we don't want to be a thin wrapper over MPI or NIC-ORented, for example. So we really want to identify what are the fundamental components in the different communication libraries. So we don't want to have an API where we pass, for example, here in send a Kokkos view, account, data type, destination tag, and communicator object. We want to try to wrap some of these, eliminate what's not needed. So with the view, we can determine automatically the count and the data type at compile time. So that can be removed from the API. We also are able to do MPI communications without tags. So we remove it as well. And for example, in NIC-ORented, you don't have tags anyway. So it allows us to have a generic API that works with different communication libraries. So the core API of Kokkos Comm is very much inspired by the minimalism of NIC-ORented. As I said, it's built with C++20 and it's fully non-blocking. So we return request objects to complete operations, very much in the style of MPI non-blocking communications. We have 2 point-to-point operations, send and receive. For now, we have 5 collectives. These were the ones that we identified as needed for the target applications that we had, but we could introduce more if needed. And we, for now, have 2 synchronization mechanisms, wait and wait all. So a quick example on how you would write a distributed matrix vector product. So here, I don't know if you can see my mouse, but we have a Kokkos Comm handle, which is an object that wraps a Kokkos execution space and a communicator object. So that would be MPI comm or a nickel comm object, for example. Then we have our data. So here, the A matrix is partitioned in a row-wise fashion. So each process has some rows of the A matrix. So we'll start by initializing, each process initializes its local part of the X vector. Then we can initiate an all-gather communication, so of the X vector. So these are the arrows describing the communication, what's happening. And at the same time, because the communication is non-blocking, we can also initialize the local part of A on each process. Then we can wait on the all gather to complete while we are initializing A. And now that all processes have their local part of A and the full X vector, we can perform the matrix vector computation. So that's for the example. So for now, Kokkos Comm supports 2 backends. First, of course, MPI. It's supported in the core API that I described earlier. So for now, we are missing GPU support on non-blocking reduction collectives because not all MPI implementations support it with the GPU awareness enabled. We have also several extensions to just the core API with the MPI backend. So we have communication modes for send operations. We also have channels, which are the abstractions that allow us to implement persistent and partition communications. So this is in development at Tennessee Tech, University of New Mexico, and I believe also a little bit Ascendia. And we are also exploring for the MPI backend stream triggering, also in development at Tennessee Tech. We also then have the nickel backend. So this was a contribution that was largely led by CA. I've done most of the implementation work on that. It's very much stream triggered in its approach. So it's basically a wrapper over nickel. So nickel operation take a stream, and that's why it's stream triggered. And this allows us to bypass some explicit synchronization between Kokkos operations and Kokkos Comm with the nickel backend. So it's been available in the core API since late October. For now, it's behind the experimental namespace. It's functional, but it likely needs more testing. So you have here on the right a table that summarizes all the features of Kokkos Comm. Sorry. Now for some ongoing work, we are trying to finish implementing non-contiguous data handling. So for now, send and receive as well as reduce are supported, but we are missing some of the collectives. So all gather, all reduce, all to all, and broadcast. These should be coming pretty soon because we have all the code infrastructure to implement that. For now, views that are of rank higher than 1 are not yet allowed in collectives. We had lots of discussion on what is the meaning of running, for example, reduce operation on multidimensional data. So we have, now that we've come to some consensus, we have a PR that is open to lift this constraint, and the expected behavior is that the library will treat it as one big 1D buffer. Then we have some work on MPI host staging, so it's not yet fully smart. Whenever the view isn't accessible from the host, we perform host staging, regardless of if the MPI is GPU aware or not. And our solution for now is that we have a CMake option that lets users specify that the MPI that they provide is GPU aware. We have a paper that has been submitted at the PASC 2026 conference. You have the screenshot of the first page here on the slide. Review notifications should be coming in about 2 weeks, so hopefully it will get accepted. Now some future work. So we want to extend Kokkos Comm with other communication backends. So first, device-oriented libraries. We have NICL for NVIDIA hardware. We want to implement a recall for AMD. This should be pretty easy to do because both libraries share the exact same API. Recall reused the NICL's API to the name. So when you're calling recall, you're calling a NICL function. Should be pretty easy to integrate, and we probably could reuse the existing bindings that we have for NICL for that. So this is in progress. And to complete the Kokkos stacked diagram that I had earlier, we want to also have support for Intel's oneCLL library, which is very close to NICL and recall in style. The API is a bit closer to MPI with much more parameters, but the interface itself is pretty small and fits very nicely with the Kokkos Comm core API. Then on the interconnect or more network-oriented libraries, we want to explore a Portals 4 backend. So that is the low-level API that is used in the Atos BXI and HPE Slingshot interconnects. And at CA, we have a project also on exploring MPC low-com, which is the intermediate communication interface that sits between MPI and the low-level network layers. So it's very similar to OFI. Then we also want to explore some execution semantics. So first on stream triggering. So we are exploring that with the NICL backend, but how it would work on MPI as well is a question that we need to answer. Basically, it would allow to eliminate some explicit synchronizations when we leverage Kokkos execution spaces. So, for example, in this code, the all-gather operation is enqueued on the same execution space as the parallel for here in 1. So because they are stream ordered, we know that the all gather will only start once this parallel 4 is finished. We don't need any synchronization in between. Here on 3, this parallel 4 is on different execution space, so it can run concurrently with these two first. However, if we want to re-enqueue some work on the execution space 1 here in 5, we need to wait on the all gather to finish, because there are some, in the case that you have non-contiguous views, if we are doing some packing and unpacking strategy, then we will need to wait for the communication to actually finish to make sure that the views have been copied back in the unpacked view. The packed view, has been correctly unpacked in the view that was passed in the all gather call. So this still has some limitations, and that's why we want to go further and explore stud execution, which provides a senders receivers API So this is in C++26. It's very similar to CUDA graphs. There are multiple reference implementations. So you have studexec by NVIDIA, you have Pika by HPX, as well as Bayman execution by the Bayman standard. And basically, it allows to express dependencies between operations in the form of a directed acyclic graph. So here in this example, on the left, you have the code that you would write today. You would initiate an MPI receive here, non-blocking MPI receive, as well as the kernel, record that kernel in an event, and then you would synchronize both operations differently. So MPI wait for the MPI receive, and could I even synchronize for the kernel. And with the stud execution, you would be able to write a transform MPI, for example, which initiates the MPI call, as well as then with stream that initiates a kernel, and the when all functions, you pass the two senders, so sender receive, and sender CUDA, and when both of these are finished, completed, you can resume execution with something else. So some other planned or ongoing efforts. So we're trying to integrate Kokkos Comm in the Trilinos framework, and more specifically in T-Petra. This is work that's being done at Sandia for now. We also want to try to work on overlapping communications and data transformations. So trying to do on-the-fly transformation of multidimensional data layouts. This is closer to my PhD research. For example, you could imagine having a 2D Kokkos view on the CPU, wanting to send it to a distant GPU. On the CPU, probably your view is stored in layout right, which is optimal for the CPU. But on the reception GPU, the GPU you're trying to send your data, you would want to have it in layout left because it's more, it improves memory access patterns. So we could imagine having the transformation of layout from layout right to layout left during the communication to improve performance. So this is something that we want to work on. Finally, also this work of Kokkos Comm is very much a test bed for exploration. So it could serve as some reference work for standardization efforts. How do we support multidimensional data in libraries such as MPI or NIC-OL? And could we use this work as well for designing a modern C++ API for the MPI library, or standard, should I say. So we'll now conclude. So what Kokkos Comm provides? It's a very lightweight library that brings you Kokkos native interfaces for explicit communications in distributed applications. It's a generic asynchronous API that is able to target multiple communication backends with support for MPI and NIC-OL, as well as more backends that are coming in the future, and especially a deep integration with the Kokkos execution model. We have a very minimal interface that leverages modern C++ implementation techniques, and that is designed to be easy to use and hard to misuse with near zero overhead. Kokkos Comm handles all the pain points that appear when you're trying to do Kokkos plus any communication library. So we handle GPU awareness, non-contiguous data, and the lifetime management of views. So if you're interested in collaborating with us on Kokkos Comm, you're welcome. For now, we're really interested in having people that want to try out Kokkos Comm in the real world. So if you're trying to write new Kokkos apps and mini apps and that you want them to be distributed, consider Kokkos Comm for doing that. If you have any Kokkos plus MPI codes that you would want to port on Kokkos Comm to do Kokkos plus Kokkos Comm, we'd be willing to help on that. And also we have the question, are there any obvious interfaces that are missing that you would absolutely need to do your reporting or implementation work? We're interested in that feedback. We also want to have some help on designing what's next for Kokkos Comm. So during these past 2 years, we are now seeing that we have some need to do some initialization and finalization work that is generic so that we can eliminate any MPI specific or NIC specific code from a Kokkos Comm application. So we also want some help on exploring other communication backends, improving or designing how we do error handling. So now most of the error handling is limited to the Kokkos Comm bindings that bind between the high-level API and the low-level MPI or NIC bindings. So we would like to improve that for users of Kokkos Comm, and also, as I mentioned, explore some senders receivers based interface for better execution semantics. Finally, if you want to help on the general development of Kokkos Comm, so implementing tests or enhancing existing ones, helping with writing benchmarks, good examples, helping improve the contiguous integration framework that we have, or help with code reviews, you're welcome. And we also need, of course, help on improving documentation. There's been lots of code that has been merged in these past month. So if you want to help us on updating the documentation accordingly, you're welcome to do so. You can join the conversation on Slack, on GitHub at the developers meeting for that. So I have some links here that you can screenshot if you want to help. So that's it for me. If you have any questions, you can ask. I'll be happy to answer. I'm putting back the links so you can have a look while we ask questions.
Thank you very much, Gabriel, for this presentation. We have time for a few questions, and I saw in the people attending that we have also other developers of Kokkos Comm, so feel free to answer if some question is more about your work. And by the way, I will add another link in the chat. It's the link to the HPSF Community Summit that will happen in the end of February in Germany. And the call for paper is still open until I think the end of the month. And you can apply. There will be at least half a day about Kokkos and half a day about Trilinos and so on. So that might be also a good place to discuss Kokkos and the global Kokkos ecosystem.
Can I ask a question?
Yeah, of course.
Hi, I'm Luca from Sandia. Nice presentation. I have a question. So at the beginning, I saw you mention like some of the issues that face codes that use Kokkos and MPI, and one of them was the necessity to pack and unpack this common pattern. But maybe I missed it. I didn't catch anything on that subject in your presentation. Is that something that is out of the scope? Is that something that you guys want to tackle later? I find like that's the code that causes tons of duplication across processes. Sorry, project, not processes.
Yes, so that's mainly the approach we've chosen. We do pack and unpack of Kokkos views. That's what we identified as the most performant solution. I think we also have some work. I know that we have benchmarks on that with the MPI data types. So creating custom MPI data types for non-contiguous views. And from what I remember, it was much slower than doing non-packing. So we create a contiguous view, pack into it, pack the non-contiguous data into it, then perform the MPI or nickel communication, and then do unpacking.
So what do you mean with packing? Are you just talking about there's a view with non-contiguous data and you just pack it in a contiguous one? Or
Yeah,
like I only need to communicate like a subset of the entries of the views?
for now, the strategy is to pack all the non-contiguous data in a contiguous
I
view
see.
and send the contiguous view in one go.
Oh, I see. Okay. And sorry, follow up with this. Like, is the communication always to send the full view, not subsets of the view? And right?
Yeah, it's the full view. It's all
Okay.
the elements of the view that is being
Okay.
passed.
Thanks.
Yeah, but you can send a subview and we will send
Yeah,
only this element.
of course. Yeah.
It's the in Kokkos a subview is also a view and we just take a view as argument.
Right. It's just
Uh,
that I have a lot of subsets of the view that I need to send, and so I can't just create like many subviews. So
yeah, we don't have a collection of subview yet.
okay.
So there is other question. So we will begin by with Mark.
Oh, hi, Cedric. Thanks, Gabriel, for the great talk. I appreciate it.
Thank you.
Nice overview. Yeah, I just wanted to ask about semantics of non-blocking communication in your wrapper. I know you just mentioned that when you get a non-contiguous view, you pack it and send one message. Do you intend to reserve the freedom to send it in multiple messages?
Yes, probably. For now, we don't have any code that would not pack, just send the contiguous chunks in multiple little packets. But that's probably something that we want to explore. So how we would uh, how this would interact with the non-blocking behavior, we don't have explored that yet.
I guess the reason I ask is because the MPI has semantics around message ordering for non-blocking
Yeah.
communication. And if you split one message into multiple messages, that may interfere, may break some of those expectations about message ordering. And so I think that's not necessarily bad, but it's something to watch out for.
Yeah, for sure. We are using internally a tag, so for the MPI communications. So we probably need to use multiple tags in that case, so that we can reorder communications on the receiving end. But that's not something that we've explored seriously for now.
Oh, yeah. I mean, MPI, yeah, I'm prepared to speak at some length about that, but not now. There's another related question, which is because you pack non-contiguous views, does the packing happen asynchronously? Like, is the user's expectation that the packing happens immediately when you call it and the message happens later, or can the packing happen later as well?
The packing happens directly. So when you return from the Kokkos Comm call,
Yeah.
the packing has happened already, although the communication has just been initiated. It's the same semantic as when you call any non-blocking MPI call.
Ah, but
So
it's not the same semantic because when you call a non-blocking MPI call, nothing may happen. But anyway, that's fine. Now I understand how the library behaves. So thank you for the presentation. I appreciate
Yeah,
it.
yeah, but I want to complete, for example, for things like nickel, where we will do also packing. we can just submit the kernel that will do the packing. So
Right.
we can be asynchronous. We don't promise to be asynchronous, but we can do it.
Okay, that's good to know. Thank you.
We have other questions. So Keigo, can you go next?
Greeting from Japan, 1 a.m. So in the later table of the collective communications, I think reduce scatter was lacking in the tables, but I feel reduce scatter is very important API. That's as important as all gather, because if you reverse the order of communication graph of all gather, you reach the reduced scatter. So especially for tensor parallelism in machine learning, reduced scatter takes very important place. So I'd like to emphasize that the reduced scatter is very important API for collective communications.
Thank you very much. In fact, it's the kind of information we need because I think it's related to Andrei's question in the chat where he was asking if Kokkos Comm is used right now by some libraries. So not yet. At CA, we have newer code. So we are currently writing new code using Kokkos. So it's a good place to start with a new library. And but we don't know exactly all the use of all the needs of our users, and we want to have some feedback. So thank you very much for the reduced scatter remark.
For example, broadcast and reduce has some duality. If you reverse the communication order of the broadcast, you reach reduce, or gather scatter makes also duality, and all gather and reduce scatter also makes dual.
Yeah, thank you for this comment. We have another question from Evan. Can you? Oh.
Can you repeat the question?
I saw a sign that you had a question.
I didn't have a question.
Okay, so
Oh.
it was Evan Weinberg. Okay. Well, okay. There is also another question in the chat by Bryden about.
Sorry, I was
Okay.
muted.
Okay, so go ahead.
My bad. Well, first off, really nice talk. I really appreciate it as someone who hates dealing with MPI. In the spirit of MPI headaches, and I'm sorry if I missed this during your talk, is there a way to pass in a staging buffer when you have to do manual packing and unpacking? And I have a motivation for that question, but I'll start with your answer first.
For now, we don't, but we probably could think about some mechanism so that the user can pass the staging buffer, because we are using one anyway, so it wouldn't be too hard to change the implementation details to allow that.
Yeah,
It would.
I will complete. I think, in fact, we want at the end to allow the user to pass its buffer to have this lightweight API. So you can go ahead about the use of that.
Yeah, well, I'm more thinking about experiences with performance and functionality headaches. So one thing that came up on both Summit and in Perlmutter, where if you pass a buffer allocated by CUDA malloc async. So this is very CUDA specific right now, to Summit MPIs or now Cray MPI, it would just explode on you. And there are various, at some point a change was made in Kokkos to stop using CUDA malloc async, but that was because we didn't have a choice. And one workaround could have been just handing in a custom CUDA malloc, like unmanaged, unfortunately, view as the buffer. So that's just one of many motivating use cases.
Yeah, in fact, the reason we have not done the API yet is there is some thought on the Kokkos side to know how to deal with memory allocation pool. So there is some work to plug Empire with Kokkos and to have this concept of memory pool that is needed to use CUDA malloc async properly. So yeah, it's really something we want to deal with, but I think Kokkos is not there yet. And as we rely on Kokkos, it's a little bit harder for us to think about that.
No, this is great. Thank you.
Thanks.
Thank you. So we will do a last question. That's a question from Brandon in the chat. He was asking for performance numbers and comparison between the different backend. And can you comment on that, Gabriel?
Yes, so for now we don't have any comparison numbers on between MPI, Nickel, etc. We have some backends. I only added, so I have it in here, only some overhead benchmark on Kokkos Comm versus MPI. So it's on the latency, how much overhead we introduce with Kokkos Comm. That's the only plot I have in my slides, but we have some numbers, some other benchmarks that have been presented in the paper, but for now we don't have any comparison between benchmarks on all operations provided by Kokkos Comms we don't have, and we don't have also comparisons between the different backends. But that's work that we are planning to do, and hopefully, if you're at the HPSF Community Summit, we probably will have some numbers to present there.
Okay, thank you very much. There have been another question about API. So just briefly, currently we don't deal with barrier because we wanted to not start library for, I would say, parallelisms by doing first a barrier. But we will have a look at algorithms that exploit the non-blocking barrier semantic. And I know it's useful also on particle simulation algorithms. So it's not out of scope. We don't have this yet because we don't have the user yet. Okay, so thank you very much for attending this session on on such a short notice. And I think the schedule for the next 2 months is already done. So please keep in your calendars, and in the next 2 months there will also be some Kokkos Tea time. Thank you very much. Have a good day.
Thank you all.